Okay, should we put another phrase?
Yeah.
What should the phrase be? Shelly?
Blue jacket.
Blue jacket is the phrase.
Phrase should be
We're going just straight up blue jacket. We're just going straight up blue jacket. That's the phrase you can put in tonight. Here we go. And here is our task at hand. Okay, so what we've done so far is we found area bounded underneath the curve, and we've also found area between two curves. Today we're going to do something super cool. Something you never really thought was possible. Here's what I want to do. I want to take this area that we see right here, bounded by this function, and here's what I want to do. I need you guys to help me visualize this. I'm going to take this and I'm going to flip it around the x-axis. So make sure you understand this, because this is the question I get from people like, I don't even know what that means, or I don't even know what that looks like. It's tough for some people to visualize. Some of you guys will see it right away. Others will not. We want to take this shape, and what we want to do is we want to rotate it around the x-axis like that. We want to spin it around. What kind of a shape would you get if you spun it around? Can you describe it at all? If I spun it around and sat it upright, wouldn't it look something like that? Yeah? Maybe? Yeah, so I'm going to spin this around the x-axis to create a three-dimensional shape. Okay, so I'm getting some like ahas. Can I see what I'm talking about? I'm going to work hard to draw it again. I'm going to use just a little bit different approach. And I'm going to do what we did before, which is I'm going to draw a rectangle for area. Does that have horizontal width or does it have vertical width? It has horizontal width of dx, doesn't it? And what I'm going to do is I'm going to take that rectangle and I'm going to spin it around. And when I spin it around, I'm going to get this. Like if I just spun the rectangle, that's what I get, wouldn't I? I'd get like a slice of this thing. I'll do it again. You can draw the rectangle in multiple regions. I'll draw one here. Again, dx. If I were to spin that around, I'll do the front and the back and see if that helps at all. Spin the front. Spin the back. Can you kind of see that shape developing? And so the idea is that we have these little kind of discs, don't we? It's almost like a quarter. Has like very thin width, doesn't it? Yeah. And so what I want to do is I want to find the volume of just one of those shapes. And so I want to find the volume of this guy. Just one of the shapes. And remember, it started by spinning that rectangle. And what did we say was the width of the rectangle? Dx. So the width is dx, but now I'd like to find, so remember that if we want to find volume of this shape, we would take the area times the width, right? How would you describe the area of a shape like that? Pi r squared, right? Yeah, we got a circle, right? So we would take this, we'd say pi r squared. And so the area or the volume of one of those is pi times r squared dx. That's the volume of 1. We don't want 1. How many do we want? So we just slap on an integral. Question. Well, this is technically a cylinder because it has width to it. You know what I mean? Like if I put it flat, it would kind of look like that. If I want to find the volume of that shape, I take the area of the base and multiply by the height, right?
Yeah, but like why is it a cylinder and not like a cube?
Because I'm taking that rectangle in the middle and I'm
Okay, I got it.
see it? Okay. Thank you for asking the question. And then I'm going to integrate it from A to B. So that's how we can find that. Now, here's the cool part is that we know what the radius is. The radius is the distance from here to here. And notice how it's bounded up above by the function. So therefore, the general formula for volume is pi times the integral from A to B of f of x quantity squared dx. You can put it on the outside or the inside. Traditionally, we would just put any constant on the outside. And so we'll do a couple examples, and they work out quite nicely. It says find the volume of the area bounded between y equals the root of x, x equals 4, and x equals 0, rotated around the x-axis. So I'll draw the shape. What does the square root of x look like? Good. And I'm going to bound it from 0 to 4. So I'm going to take that thing and I'm going to rotate it around the x-axis. So I'll put a couple slices in here so hopefully we can see it. If I were to slice it like that and rotate it around, I'll do the end here. I'll rotate that around. Maybe I want to describe what shape we'd be getting. Can you see that three-dimensional rotation? Come on. Cone? Sure. A bullet? Yes. Half of a football. We all on the same page? See what you're getting? Awesome. So what I want to do is I just want to find the volume of one of those things. And the volume of one of those things, what I do is I have a disk. And the way that we find the volume of a disk is we find the width, which is dx, times pi r squared. Why pi r squared? Because pi r squared is the area of a circle. So this thing right there is r. What determines my distance from the x-axis to the function? Just the function. So for example, if I was at an x value of like 2 right here, then the height would be the square root of 2. If I chose an x value of 3 here, then the height would be the square root of 3. We just take the x value and plug it into the function that gives us our height or our radius. So the radius is equal to the square root of x. So the area or the volume of one of these things is pi times r squared, or square root of x squared, times the width dx. That's the volume of 1. We want an infinite number, so what should I do? Put on an integral. Where do you think we bound it from? 0 to 4. And now the problem becomes easy peasy. What's square root of x squared? x. So we have pi times x integrated. Whoop, I'm sorry. Sorry about that. Pi x integrated 0 to 4 dx. What is the antiderivative of x? Yep, so pi times x squared over 2, evaluated at 0 and 4. We can see that if you plug in 0, you get 0, but if you plug in 4, what do you get? 8 pi. That's the exact volume. Really not too bad, is it? No. Find the volume of area between y equals x squared plus 1, x equals 0, and x equals 2 rotated around the x-axis. I want you to take a minute and see if you could just draw the shaded region. Just see if you could draw kind of the shaded region that we're going to be rotating, okay? Just try to visualize it. Go, take about a minute. Kind of a tough deal. All right. So we've got that shape. You know, is that the area? Is that kind of the region that you drew? What if you tried to describe the shape? Would you what would you come up with? Three-dimensionally? Anybody? Yeah, sure. Megaphone? Yeah, if you kind of stand it upright, you kind of get that thing going on, right? I kind of think of it like a stand for a potted plant or something. I don't know. Volcano. Yeah, I like thank you. Volcano. I like it. Pizza Hut. Let's go. All right. What's the width? Dx or dy? Dx. And then we have pi r squared. What is going to determine our radius? Our radius is equal to what? Yep, the distance from the x-axis to the function is x squared plus 1. And so therefore, my integral will look like this. Pi times x squared plus 1 quantity squared dx. I don't want to do one of those. I want to do an infinite number. Bounds of integration, 0 to 2. So let's square that out. I'm going to have pi times the integral from 0 to 2 of what? If we take x squared plus 1 and multiply it by x squared plus 1, x to the fourth, 2x squared, good. So now we take the antiderivative, which will be x to the fifth over 5 plus 2x cubed over 3 plus x evaluated at 0 and 2. We all good with that? Kenzie? I plug in 2. I get pi times 32 over 5 plus 16 over 3. Smartboard just got stupid. And then plus 2 on the end there. Now at this point, you could plug in your calculator, or you could go ahead and find common denominators, which would be 15. So it would be pi times 96 over 15 plus 80 over 15 plus 30 over 15. 206 pi over 15. And sometimes people do mistake, they forget to put the pi on there.
Would you like specifically times those and by pi, or would you rather have?
Yeah, so I will accept your answer in terms of pi or written wholly as a decimal. But I will say one of the biggest mistakes that I make when I go through and I do the AP exam questions is I forget to put pi on my answer. Because very often they have a kind of really nasty number, like say that number's like 17.134, and then I I forget to put that on the end, or to actually multiply it by pi. So make sure you have that in there. Okay. All right, last one for the day. Find the volume of the area bounded between the curves y equals 1/2 x plus 1, x equals 0, and y equals 3 rotated around the y-axis. What makes this one different? Y-axis. 1/2 x plus 1. So I start there, and then I go up 1 and over 2. So I kind of try to draw my line, something like that. And it says x equals 0, which is this vertical line here, and then y equals 3. Ooh, y equals 3 looks like that. So that's my region. And notice how instead of rotating it over the x-axis, we are rotating it over the y-axis. So instead of drawing a vertical rectangle, I'm going to draw a horizontal rectangle. What's the thickness of that rectangle? Is it dx or is it dy? It is dy. Okay. So I have dy, and then I need a radius. Now, wouldn't you want to say that the radius is 1/2 x plus 1? That's our function. Only the radius can't have what variable in it? X. What variable do we have to have instead? So how do we write this so we have y as a variable instead? Now, y minus 1 is equal to 1/2 x. And then what do we do? Times by 2. So you have 2y minus 2 is equal to x. If your radius, instead of 1/2 x plus 1, your radius is 2y minus 2. So we have pi times your radius squared dy. That's the volume of one of those discs. We call this discs right now. That's a slice of our shape. I would like to integrate. We want to take a stab at the bounds of integration. Should my bounds be x values or should they be y values? They should be y values. Please focus on this. This is the point of confusion. Look at my original area. The original area is in red or in green, correct? When you look at your original area, you want to select the y values of your original area. What are the y values of the original area? 1 to 3. See that? All right, just a little bit of algebra now. We have the integral set up. 2y minus 2 quantities squared. Somebody square that out for me, please. 4y squared minus what? 2y? 4y? I'm going 8y. Because you have 2y times negative 2, and then another 2y times negative 2. That'll be a total of negative 8y, and then plus 4 on the end of that. Evaluate it, or I'm sorry, dy. Can I give you an option? If you'd like to, you could put this 4 all the way out there. Would you like to, or do you just want to leave it? Okay, we'll leave it. We take the antiderivative of 4y squared. 4y cubed over 3 minus 8y squared over 2, or 4y squared, plus 4y. Notice how I don't have a 0 on the end at this time. As I plug in the 3, I'm going to be very careful. Take my whole expression, multiply it by pi. 3 cubed is 27, divided by 3 is 9, times 4 is 36. 3 squared is 9, times 4 is 36. Oh, look at who wrote that problem. Minus 12. Now I will plug in 1, and I will get 4/3. It is plus 12. Thank you. So this problem actually works out quite nicely. Notice how the 36's cancel. Notice how the 4's cancel. And we get 12 minus 4/3, or 36/3 minus 4/3. What will that give me? 32 pi over 3 is that exact volume. I'd like to end by just showing you this one statement. Anybody volume of a cone? Volume of a cone is 1/3 pi r squared h. You once upon a time learned that, right? Just think about it, folks. If you just think about a cone, how did they determine that that's the formula for the volume of that cone? I mean, it's not very intuitive. It's not like a cube or a cylinder. It's kind of an odd shape, isn't it? All of our formulas that we have for volume, most of them that you've got from geometry, they can be proved using the calculus that we have. What did they do before the calculus? Archimedes had an incredible principle that he used to solve this stuff. And I'm not even smart enough to be able to follow the first 2 steps of the process he used. I've tried for hours. He did it thousands of years before we ever did. People were amazed. They would ask him to write letters to explain his work. The only problem is he would respond and nobody could understand it. Absolutely amazing, but we could do it pretty simply using calculus. He had another method and he used the lever and stuff. It just blows your mind. But anyway, there you go. What was the phrase for today again? Blue jacket. We'll see what we get.